Whenever you see a question with a circle and stuff happening inside with angles and things, it's almost certainly going to be a circle theorems question. So you need to know your circle theorems, else you haven't got much hope really, it's got to be said. And these are the circle theorems that are covered on this specification. There's quite a lot of them. First of all, I think I'll start with this one on left here. If you have like a semicircle, basically, if a line goes through the diameter, then the lines come off it will meet at 90 degrees. You can prove this using isosceles triangles. Actually, isosceles triangle underpin all the circle theorems. Actually, most of the circle theorems. It's only a very brief explanation. You can also show that if you have lines going to the center, then this angle at the center is twice that at the circumference. So if this was 40, then this one would be 20. Again, you can use isosceles triangles. And a consequence of this, if you were to like draw another one like so, but then remove the green one, would be you'd get something that looks like this on the top left. Angles in the same segment are equal. This one is. I've spoken about that. Another good one is cyclic quadrilateral. If you draw any quadrilateral inside a circle touching the circumference, the outside, then the opposite angles here will add to 180 necessarily, okay, and as will these two. And then we get to slightly more technical ones with tangents and chords. This is a good one. The tangent will meet the radius at 90 degrees. I personally think that's kind of the easiest one to remember because what else could it be really? Like it looks like 90, where it's very hard to draw a diagram that's not to scale and not to still look like 90. It will always look like that. This one here, we've got the radius meeting a chord. It also meets at 90 degrees. That's useful in certain situations in maths. And then the hardest one, I think, is it's called the alternate segment theorem. It doesn't say that here. But if you have a tangent where it touches the circle, if you draw a triangle, then this angle here will equal this angle here, and the red one will equal the red one. I sort of follow the line along and see where it gets to. It's quite easy to mix up which one's which sometimes, I think. Okay, so back to this question, we've got to think about which one we're going to use. And actually, we basically have an upside down version of the top left one. Maybe you can see it. I normally draw the circle theorem like a bow tie, okay, because that's all you need really. These two are equal. So if you ignore BC, we've actually answered this first question. This is also going to equal 58 degrees because of these top two on the bow tie. Angle ACD is 58 degrees. Angles in the same segment are equal. There are sometimes like other words you can write instead, but for me that's the easiest one to remember. I think I've read in the mark scheme about it being angles subtended. I've forgotten what it actually was, but angles in the same segment are equal. That's what I would go with. Okay, now we're interested in angle ACB. So it's this one here. A bit more difficult to spot because there's no like bow tie like so. So we maybe need to start thinking what other circle theorems have we not used? Well, there's no tangents in sight. There's no chords with radiuses going to the center. So I can rule out these three here. There's no quadrilateral. Okay, is there an angle at the center? Well, there is a center, but there's no angle at the center. So but there is a center. So it's going to be the other one. It's going to be this one here. The angle in a semicircle is 90 degrees. Okay, I've got a line here. Basically, this will be 90 degrees. And if I'm showing my reasoning, that should be the first thing I write down. Angle ABC equals 90 degrees. Angle in a semicircle. What next? Well, I want this one. I kind of see a triangle now. I've got a triangle here. And I'm going to use another one of the same segment. Because this is 22 degrees, then these two are also equal. And I can say that this is 22 degrees. Angle B AC equals 22 degrees, same segment. And finally, we've got a triangle. I've got 90 degrees here. I just want to find this one. So angle B. Wait, it's asked me for ACB. It's the same thing, but ACB is going to be 180 minus 90 minus 22. It's 68 degrees. Now, to be honest, I'll probably get away with not writing a reason down because I've written 2 reasons, but it's best to give all your reasoning. So angles in a triangle add up to 180. So learn your circle theorems, practice them, practice recognizing which ones to use. If you know them well, then it kind of sometimes jumps out at you. Sometimes you just got to maybe try and work out as many angles as you can, and it might come together. Like, let's imagine that I'd sort of forgotten that right-angled one. Well, I could work out that one, and then I could work out that one because it's the same, they're opposite. I could work out that one, I could work out that one. And if I'm given reasons, I could still maybe get some marks. I think actually, ultimately, I think this question's impossible unless I do use the 90 degrees, but sometimes there's more than one way. I could even, if I was desperate, maybe start drawing isosceles triangles to the center. That's probably going to make it more confusing, but at the end of the day, that's how you prove these circle theorems.